So here's the thing, this orange dot here on the application, this indicates that it is actually recording. If that dot goes away, I may not see it right away. Occasionally something happens if I go to a web page or if I pause the presentation for something. Sometimes Echo hangs up and stops, does that. If the orange dot goes away, let me know, because there's going to be a big gap in the lecture otherwise. Okay? So you guys can all help. Okay. So we'll see how far we get on this. This first topic is Facebook's photo management system. Okay. Before we talk about how Facebook manages photos, we're going to talk about how memory gets handled, how systems deal with problems when they get big, things like that. But we will pretty soon get to Facebook's photo management system. Okay. So what we'll cover: system scale, capacity, and big data, different types of memory, and then Facebook's Haystack system. Haystack is the system that Facebook stores its photos in. And more generally, we'll talk about object storage systems as well. And then a little bit, we'll introduce standard types of databases called a relational database. Okay, and then Hadoop is a big data crunching operation. Okay, so first a little intro about Facebook. So Facebook's size is very, very big. Because it's very big, it has a lot of inertia as a social media app, right? People stay on it because their friends are on it. And at this point, because there aren't that many new people joining the internet these days, it makes it really harder for a new competitor to bump in. So, for example, back in the day, we'll draw a little chart here. Okay? And we'll do a curve of internet adoption. We'll have it be... Oh, shit, this isn't going to work as well as I thought. I gotta shrink this down. Okay, so there was a window where internet was exploding. I gotta do a two-part here. Okay? And then there was another window where it really tapered off. There we go. That looks about right. Okay, that'll do. All right. So in this window, and let's say the break point here is about 2005. So 2005, well, over here we'll have 1995 and 2015. Okay. In this little window here with social media adoption, if Facebook share is like this, and MySpace's share is like this, I'm still adding on a whole bunch of people in the next couple years, right? So if MySpace is good, but not good enough, and people aren't really adding it, right? If MySpace is going up, like to catch a little bit more market share, but not much, but Facebook is catching most of that new growth, right? And Facebook's up here. If there's a system with a better product, there are so many new people joining up that I can just capture those new users and outpace my competitors, right? But by here, right, if Facebook is here, even if some other new operation comes up and they're so much better than Facebook, there's not that much new growth to capture. Even if they capture all the new growth, they're going to be like this, and Facebook is still going to be like this, and they're not going to catch up. Okay? So at this point, since there aren't that many new people joining the internet, joining social media, Facebook is pretty well ensconced. Okay, it's going to take some really bad event, like you find out that Mark Zuckerberg has been using your information to run a human sacrifice cult or something. That's basically what it's going to take to dethrone Facebook at this point. Okay. So, but having said that, Facebook isn't invulnerable, right? There are things that could hypothetically go wrong. I mean, Facebook is good enough that it's probably not going to happen, but you never know, right? So, for example, if pages start loading really slowly, or if they have security issues, right? Something like that might cause mass defections, right? Other kinds of improvements on Facebook's model, they might have a better interface, better data constraints, privacy, better security, better content filtering, better, more relevant ads. It's theoretically possible that somebody could come along and do a better job than Facebook. Chances are it's not going to happen anytime soon, okay? Anyway. Every now and then you hear about some new social media that's supposed to get a lot of buzz, and they'll say, oh yeah, they keep your data more private. Well, if they keep your data more private, how are they going to make money and keep offering their own operation for free? probably doesn't work that well. Anyway, still, like I said, Facebook has to try to keep ahead of potential competitors, so it needs continuous innovation. And one of the big things is managing huge and growing scale. The fact, the big data repository in Facebook is images, right? Every image could be like 2, 5, 10 megs, and people are uploading hundreds of millions of those every day. So that's a lot of data. Basically, Facebook is dealing with like a truckload of hard drives every day worth of data. So, as you might know, Facebook is the world's biggest social media application. Recent numbers, these are from within the last 12 months, 2.3 billion users and 1.6 billion daily users. 300 million photos uploaded every day. This one is old. It might be a little off, a little high, a little low, but about 20% of US page views happen through Facebook. Like, people go to visit a page, they did it because that link either appeared in a friend's post or it appeared in your feed, whatever. People find the links on Facebook and they go there. So Facebook is a big source of site traffic. Okay, and there's some more, other stuff there, but you don't have to memorize these. These are like kind of trivia things just to give you an idea. Facebook is really big, right? I'm not going to ask you, does Facebook have 2.2, 2.3, 2.4 monthly visitors? That's silly. We know Facebook is really big, right? 2.3 users is, I don't know, probably something like a third of the world's population, right? A little less, but maybe like 30%. Anyway, and then what about peak traffic, right? When Facebook is busy, some of the peak times are like early evening, and in the North America, it's just after the lunch hour is where everything peaks. So then that 1 to 3 p.m., I guess people get back from lunch and they're bored at work and they want to see what's on Facebook. So that happens. Anyway, activities that are simple on a small scale really do require specialized systems at Facebook. So, simple example. You guys have used Excel. How many rows can an Excel file hold? If I fire up Excel and I want a packet full of data, how many rows can an Excel worksheet hold? Anybody know? Ballpark number? I'll give you a hint. In the old version, in Excel 97, the number was 64K, so 65,000 and small change. It's bigger now. It's about 1 million, okay? It's, again, that, it's an even K, so 2 to the 20th. But if I fire up Excel, which I can do, and show a blank workbook, boom. If I want to scroll all the way down to the end, which I can eventually do, okay? Eventually I get some crazy big numbers. But I'm not going to go all the way down to 1 million. I have to, But trust me, you can hold 1 million records. But let me ask you this. Suppose you're Facebook and you have 2.3 billion monthly users. Can you put those all in one Excel worksheet? No, you can't, right? You can't just buy this kind of off-the-shelf software and have it work for you. You need a special system, okay? Other thing, suppose you have a bunch of images on a hard drive, right? What's a typical hard drive size these days? What? 1 gigabyte? 1 terabyte, right? Terabyte is a pretty 1,000 gigs. That is a pretty typical number. How many images can you hold on a 1 terabyte hard drive? Rough number. So let's say 500 per gig, so 500,000 is kind of like an upper bound. That's how many you can hold on one hard drive. Can Facebook do that on one hard drive? No, they cannot. They are uploading 600 times that number of photos every day. They're uploading like 600 hard drives. And on top of that, Facebook keeps extra copies of everything. Probably everything they keep is a triple copy for reliability. So that's like 1,800 hard drives of photo data every day. They simply cannot operate the same way as we do with single machines, right? They need specialized tools. Okay. So, talk about the photo post process. So, let me see. Good, I still have, I'm just checking my, okay, you see that. So, posting a photo on Facebook, actually, it seems simple to us because we just see the interface side, but there's actually a whole lot of stuff going on. So, first of all, when you post a photo, Facebook is going to try to, first you have to accept it, right? So, you upload, you click it, the file has to get there. Then Facebook is going to scan it for prohibited content, right? Various kinds of not safe for work content. Then, once Facebook has accepted, say, okay, this image is okay, then it's going to store it and it's going to replicate it, right? It's going to enter it into its database and it's going to make copies of it somewhere in case something happens to the original. Then it's going to distribute to other people through the feed, right? So if you upload a batch of photos, you go on vacation somewhere, you upload the photos, it's going to get echoed somewhere to other people that you know. It's going to get included and say, oh, Doug just uploaded a bunch of photos, check those out. So the ability to do those things quickly is key for Facebook's competitive advantage, right? The upload process isn't that important. If that takes a little time, people can live with that. I mean, you'd rather it be faster than slower. But if you have a lot of friends and it's all getting echoed to them, and a fair number of those friends are going to look at it, right? You're easily talking, 100 looks and or downloads for every photo. The reading process, pulling the information from the database, has to be a lot more efficient than the upload, the writing process, okay? So being able to do that quickly is good. If it takes a few seconds to upload the photo, that's okay. What people really want is for all the photos that come through that they see, number one, they get to people quickly, and number two, if you want to look at them, you're not sitting twiddling your thumbs for 15 seconds while you're waiting for a photo to download. Okay. So we can express this as a capacity problem. This capacity stuff here is about as close to math as we're going to get. We have a tiny bit of conceptual math here, and then later on, a few weeks down the road, we'll have a little bit more, conceptual math. This is not a math course. Okay. So, big picture, Facebook has to match supply and demand for aggregate user action. So, all the stuff people are trying to do on Facebook, that's user demand. And Facebook has to have capacity to meet all those demands in reasonably good time. Okay? So, for demand, you can influence it, right? Facebook can do things to try to steer people in one way or another, but you can't directly control it. You can't control what people want to see, okay? Other thing, throttling or other limitations, direct limitations, leave a vulnerability to competitors. If Facebook says, you know what, I'm only going to let you upload 5 photos a day, or I'm only going to let you look at 20 photos a day, people are going to go somewhere else, right? That kind of hard limit just isn't practical. So essentially, Facebook has to have capacity available to meet demand, because if they don't, somebody else will find a way to do it. Now, on the supply side, the ability of Facebook to meet those user demands, it's about hardware and it's about process design. What kind of hardware is Facebook using, and how is it delivering the content to the users, right? And there's a bunch of options there. We'll spend a little bit of time talking about that before it's all over. But generally speaking, whatever case you're dealing with at a time, if you want to increase that, it's going to cost more, right? If your system is absolutely shit to start with, then yeah, you can make some small changes, very low cost, massively increase capacity, but eventually you have a pretty good system in place, and then increasing that, it's going to require more hardware and or some serious thought about process design. Okay. So, basic capacity problem, right? Again, processing capacity has to meet the photo upload rate. So Facebook has to process the photos, do everything it needs to, in about the time it takes to upload all of them. So if we're putting this in equation form, that funny thing right here, right? Can you see you can't see my cursor. That is a Greek lambda, a lowercase l. Okay? So lambda is the arrival rate, the rate at which new pictures are being uploaded. S is the number of system processors, whatever machines you have to process the photos. And T sub P is the time to process each photo. So, for example, if I have 100 processors, 100 servers that are processing photos, and each one of those can process one photo per second, right? That each photo requires 1 second, then my system capacity is 100 machines divided by 1 second, right? I can process 100 photos per second. Easy, right? So, if the upload rate increases, here's the math, something has to happen. If lambda goes up, if people are trying to upload more pictures, there are 3 ways that can play out. Number one, Facebook can include more processors, right? It can say, oh, I'm going to add on more hardware in parallel to process these uploads. Or it can somehow reduce the processing time, right? It can come up with faster hardware, faster connection speeds, better organization of the system, some kind of thing there. I can drop T sub P, I can process photos faster. Or there's going to be a backlog, right? If I don't increase anything on the right, and I'm already at capacity, and then people try to stuff more pictures into Facebook, there's going to be a backlog, and people aren't going to be happy, okay? So as traffic goes up, basically Facebook has to deal with that somehow. Now, what Facebook's solution, okay, this is a very simple version. This is like the IDS 200 version of what Facebook does. Number one, they have a massive in-memory system. So basically, let's see if I can do this in Paint real quick. In-memory system is something like this, and we'll have a little bit more later on. Ooh, I can do that. Okay, so these are hard drives, or they're going to be. Make a few there. Okay. So this, RAM. RAM is fast, right? But RAM is also expensive. These are hard drives. Slow, but cheap. Okay? So, when new photos come in, and when requests go out, ideally, they're only requests for ones that are in RAM. And if the request is in RAM, it can be responded to very quickly, okay? There's a reason why when you're playing like cutting-edge video games on your machine, most of it happens in RAM. It doesn't access the hard drive unless you like go into a new region or something, okay? Unless you're downloading new content for something. But some of the requests are not available in RAM because RAM is expensive. You don't want to operate a system at Facebook scale all in RAM. It wouldn't be cost feasible. So most of the photos do get stored on hard drives, okay? And that has to be fast enough. Okay, this is the basic system of how Facebook works. The requests that come in for popular stuff, they get stored in RAM, they can be responded to quickly. The other ones, they get stored on hard drives and they, not quite as fast, but fast enough. Okay? So, that's what a in-memory system is, right? The stuff that's popular you keep in RAM and you support it with hard drives for permanent storage. Caching is simply a fancy computer term for saying, I'm keeping stuff that I need often where it's easy to reach, right? It's the same thing as like, if you have tools in your garage, the stuff you use a lot, like maybe you use wrenches and screwdrivers and a drill a lot, you keep those right inside the door. Stuff that you maybe don't use very often, like a table saw, you push that somewhere off in the back because, you know, if you need to use it, you know where to get it, but you don't use it nearly as often as a screwdriver, okay? That's all caching is. Same thing with Facebook. The photos that are popular today, right? Somebody's just uploaded and you know a lot of people are going to want to look at, you put it somewhere where it's easy to reach. And then replication. There's going to be different copies of everything. And typically, again, this kind of system, even if something is stored in RAM, you're going to have triple copies of it on hard drives so that it solves a few problems. Number one, you can have simultaneous access to the same file, right? Otherwise, people have to take turns accessing it. And just for reliability, if one hard drive volume gets broken somehow, it shits itself, then you still have a couple other copies in the system to, you know, still recover. Okay, so that's a very simplified version. We'll have more detail. Haystack is Facebook's system for storing photos. And, you know, it's from the phrase needle in a haystack. Finding a particular photo is like finding a needle in a haystack. Now, before we can really understand all this stuff about what Facebook does, though, we're going to talk about memory, we're going to talk about databases, and then we'll have a little bit of background, and we'll make some more sense. Okay. So, big data. Big data is a term that got used a lot. It's gradually falling out of fashion to say it. A big part of that is because it's inherently an imprecise term, right? When people say big data, recognize, okay, yeah, you have a lot of data, but what exactly is the problem? The other thing is it's, you know, situationally dependent. For example, a big data problem for UIC is going to be trivial for Facebook, right? Facebook has vastly more data than UIC does. And even something that was big for 1999 is pretty trivial for now. I remember in 1998, I first moved to Chicago, and I got a new desktop, and I was very excited to see that the hard drive had 6 gigs. And I thought, man, what am I going to do with 6 gigs of space? And in fact, because it was the late 90s, I never even filled it, right? I got up to about 3 gigs, and then, yeah, so anyway, because we didn't have streaming video back then, so, you know, you didn't, like, save all these massive video files like you do now. But, yeah, back then, 6 gigs was plenty. Anyway, but 6 gigs now would be pretty trivial, right? Even if I'm running a Java application, I can have almost that much memory just in RAM these days. So, working definition, though, of big data basically means you have so much data that you require some kind of special tools or system to manage. And it could be just in terms of any of one of these so-called 4 V's. So volume or velocity, right? Volume is just how much data you have. Velocity, how fast it's arriving. Variety, different types of data. So small, compact text files require different handling from images and videos, for example. And veracity, making sure that everything is correct. For example, if you keep multiple copies of all your data, periodically you ought to go around and check to make sure that everything is getting synchronized as far as updates. If one file changes, you have to make the changes in the backup copies, for example. And you have to make sure that data didn't get corrupted. So there's a little picture here, IBM, let's see if I can get to that. This is the sort of thing that sometimes drops the, yeah, we're good though. Okay, there's a little image here. If you want to check it out, this says everything I have to say and then some, even though it's a few years old, but the principles are the same. But, like I said, big data is a term that is falling out of fashion. Let's see what happened there. There we go. Okay. It's falling out of fashion. People don't use it so much because, again, it's inherently vague. If you want to talk about your kind of big data problems, you should talk about the specific problem that you have. It'll make you sound a lot smarter. Okay. So, scale measures. Most of these are things that you should know, and we'll learn a few more. So, your basic ones, kilo for 1,000, mega for 1,000,000, giga for 1,000,000,000, tera for 1,000,000,000,000, right? And terabytes are the biggest ones that we deal with every day, probably. Petabytes is the next group of 1,000, exabytes, and then zettabytes. So, different ideas of scale. A kilobyte, right, 1K be like a short text file, right? Roughly 1,000 characters, so about equivalent to 1 page of printed text. A megabyte might be a reasonably big image, right? Not like a huge one, but, you know, reasonably big in 24-bit color. So something like, you know, a few hundred pixels by a few hundred pixels, that'd be a megabyte, or 200 by 200 maybe. Gigabyte, right, a long video. So old-timey CDs, they had a capacity of about 2/3 of a gigabyte, and then DVDs had about twice that much. So a long video that was on a DVD, yeah, it'd be about a gig. Okay? Terabyte, typical hard drive in whatever machine you may have, you know, roughly typical number there. Petabyte is about 1 day's worth of new Facebook data. Okay, so again, they're literally, in effect, bringing a truckload of hard drives into their organization worth of data every day. Exabyte is about all the data of a large business. So if Facebook is bringing in a petabyte every day, then in about 3 years, they're building up an exabyte worth of photo data. Okay, so that's how that goes. And, you know, Facebook obviously has several exabytes of data. Other businesses may have a little more or less. But yeah, if you're talking about exabytes, you know, you're talking about these big operations like Facebook, Google, Amazon, those kind of places. Last, zettabyte. A few years ago, we crossed the threshold into where total internet traffic was a zettabyte. Now it's more like 3 zettabytes because it keeps creeping up. But still, it's only a few. If you're talking zettabytes, you're definitely talking, you know, whole internet kind of capacity issues. Okay? So what you should know are those prefixes and their associated numbers. Okay? And if you know the associated numbers, you can probably think of good examples. But somebody will surely come along with a snappy mnemonic to know those. But really, everybody here should know kilo, mega, giga, tera. It's these 3 that you got to know, okay, that you have to learn. All right. We'll talk just for a minute, and then we'll come back and finish up some of this on Friday. So, data management, right? There's 2 basic kinds of memory. number one, there's a question, is it permanent? Number two, is it writable? And there's actually a lot of overlap there if you think about it, because if memory is permanent, it's generally not writable. Okay, for example, think about computer chips, right? You buy them, the stuff is already on there. In principle, yeah, if you had super specialized tools, you could change what's on those chips, but we don't have that kind of stuff. So for all practical purposes, it's not writable, right? The gap is things like burning new DVDs, right? If you get some and you want to store it somewhere, you can actually burn it, and you can take something that's writable, make it permanent. By making it permanent, you've made it no longer writable. Okay, so two basic families, memory that's read-only, and if it's read-only, by definition, you can't write to it, you can't change